Mr. B. Dhanasega is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We are actually studying the various LR parsing techniques in the previous episodes. We have already finished the SLR parsing table construction and how the strings are parsed by using SLR parsing table. That is the most simplest one, but also we have seen the drawback with SLR parsing table construction, because there is no guarantee that for all the context free grammars we will be able to successfully construct the SLR parsing table. But at the same time we have seen the second one, which is the canonical LR parsing table, where it is the most complex one, which uses the LR of 1 items for the construction of the parsing table, and at the same time it is guaranteed that for all kinds of context free grammars we will be definitely able to produce a context free, there is a parsing table, that is canonical LR parsing table, and thus it is possible to parse any language provided we will be having a that is context free grammar for recognizing the language. But the problem with the canonical LR parsing table is the number of states. We will be having large number of states, and more the states, automatically the size of the parsing table will be more, and in turn it will create a larger parsing table. The size of the compiler will also be larger. But now the question is it possible to find out a parsing table which is having the intermediate power in between the SLR and the canonical LR, so that it is guaranteed that for all kind of grammars we will be able to successfully construct the parsing table, and at the same time that is we will be having that is less complexity than the complexity which we have faced in canonical LR. The answer is look ahead LR parsing table, that is LALR, that is parsing table. This is going to have the intermediate power in between your SLR and canonical LR. In between, that means the parsing table size will be smaller than the parsing table size produced for a CLR parsing table for the same grammar. That means number of states will be lesser when you compare with the CLR. And when you are looking at the parsing table construction process, SLR is using LR of 0 items and canonical LR is using LR of 1 items, and the same kernels, that is your LR of 1 items, are even used by LALR parsing table also. So if you are interested in constructing an LALR parsing table, the first thing is from the given context free grammar we need to first of all find out what is going to be the augmented grammar, which is obtained by introducing one additional production along with the given grammar, and followed by that we should go for constructing the LR of 1 items. So LR of 1 items, that will be the set of states we will be having for the given grammar. So once the LR of 1 items are constructed, then the procedure differs for LALR parsing table. As far as canonical LR parsing table construction is concerned, so we construct LR of 1 items, and once LR of 1 items are that is constructed, we have the algorithm for constructing the parsing table, and we will transform it into the parsing table so that we will be able to proceed with parsing. But here we need to identify LR of 1 items, but the constraint is having same core and merging these sets with the common cores into one set of items. So here we should know that is what is the meaning of a core. When you look at the format of LR of 1 items, it is of the form A derives alpha dot beta comma small a. That means there will be a right hand side for the production, and on that there may be a dot, there will be a dot available somewhere in that is on the right hand side, So, that is what we say that it is of the form alpha dot beta, comma the second component is the lookahead component. It is going to be one terminal, that is why we call it as this canonical LR of 1 items. So, there are 3 components, what precedes that dot and what follows that dot and followed by what is going to be the lookahead. So, the alpha dot beta is called the core, that is we call it as the kernel, and whereas the small a is called the lookahead. So, now the way in which we are constructing the LALR items is by finding the common cores. We may have different states, for example, I and j are 2 different states, but the states are differing only in terms of the lookaheads. If it is the case, then it is possible to merge these states to form a new state, so that the kernels will be same, that is the cores will be same, but whereas the lookaheads are different. So, now we can combine these lookaheads with A or B. See, for example, if you are having the state called I, where there is an item of the form A derives alpha dot beta comma small a, and there is another state called J, where there is once again an item of the form A derives alpha dot beta comma small b. So, now we find that these 2 items are differing only in terms of the core. The core is A derives alpha dot beta on both states, that is I and j, but whereas the lookaheads are small a and small b. Now, we can form a new state called ij with the kernel called A derives alpha dot beta comma the lookaheads will be presented as A or B. So, now the action component, that is we are having, that is parsing table. In the parsing table, so there will be an action component and there is a go to component. As far as the action components are concerned, they are going to be modified to reflect the non-error actions, all these items in the merge state. So, we will be having a new state called merge state, and the action for the ith state and the action for the jth state are now combined to be placed into the action of the merge state. So, we will not be losing any information, but we will be merging and the information will be available in a new state, which is the combination of the ith state and the jth state. So, when you combine this, the advantage here is we will be able to have smaller number of states than the number of states available in the CLR parser. So, we use the same items, that is LR of 1 items, and we go for constructing LALR items by combining the items, set of items where there is a common factor when you compare with the, that is cores or the kernels. So, now if you find that there is LR of 1 items do not produce parsing action conflict, then we are very sure that the union of these states, that is the merged states, will never produce any parsing action conflict. Suppose if this is not being satisfied, then there is a chance that the grammar which will be succeeded in constructing the parsing table by using CLR may fail to construct a parsing table in LALR. But that is not going to happen, because we are very sure that the union of the states or the merged states will never form any kind of parsing action conflict, and if there is no such action conflict in the LR of 1 items or in the corresponding CLR parser. So, now in what way they are different, that is CLR and LALR. In terms of the parsing behavior, that is once we know that there is a parsing table available for the LALR parser, the behavior of the parsing table is same as the behavior of your CLR parsing table, there is no difference. But the difference is whenever we have an erroneous input, as long as we have that is valid inputs, there is no problem. The LALR parser is going to parse the strings much earlier than the amount of time required for the CLR parser. But when we find that there is an error available, your CLR is much faster in declaring the error, or that is producing that error, but whereas the LALR parser is definitely going to detect that error, no doubt about that, but it takes little more time than the time required for producing the error or declaring the error by a CLR parser. So, that is the only issue we are facing with that is LALR parser. So, both parses the string in the same manner, there is no difference on that, but whereas when you that is talk about the time required for parsing an erroneous string or the time required for producing the error by the LALR parser, it takes little more time than the time required for producing the error by the that is equivalent CLR parser. So, in that way they are differing, but otherwise in terms of the parsing or the performance of the that is parsing process, we do not find out there is any problem with LALR parsing table. So, now the question is how we are constructing the LALR parsing table. The simple idea is you find out the states. If there are states like here we have a there is canonical set of item C which is having n number of states. So, I0, I1, I2 etc. up to there is In, and that is what given for us. So, now these items are actually formed with the help of LR of 1 items, or the set of states are obtained by constructing LR of 1 items, and if you go for constructing CLR parsing table, there is no problem, we can proceed with this. But now we are interested in going for LALR parsing table, but if you want to go for LALR parsing table, there is a need for finding the common kernels across various states. So, find out the common kernels, and if they are common, we should go for the merging of the states. So, the algorithm is you are given a context free grammar which is augmented by S dash derives S, and we will produce a parsing table called LALR parsing table with same routines like your auction is there and go to entries are also there. And now we go for constructing LR of 1 items which are required for the LALR parsing table. So, for each core present among the set of states, there is LR of 1 items, find all these sets having the same core and replace these sets by their unions. It is the simple procedure for finding the LALR of 1 items. That means, the LR of 1 items with the combined kernels, provided the cores are going to be same, whereas the lookaheads are different. So, now we will be forming new set of items called C dash, where we are having m number of states starting from there is J0, J1 etc. up to Jm, and we call it as once again that is the merged set of items called LR of 1 items. So, now the question is how we will be deciding the parsing actions. So, for each state I, actually there is a parsing action already defined on the canonical LR parser, and here also if you look at this look at the LR of 1 items, there is a parsing action defined for the ith state, and now we are having the new state called Ji. So, whatever be the parsing action for I, it is going to be constructed from that is Ji now using the CLR parsing table construction algorithm. The same story we are repeating. If we are having the for the ith state, whatever be the parsing action to be mentioned in your parsing table, we do it now for ith state in your J. But if you find that J is the union of I1, I2 etc. up to Im, then the cores of go to of I1 comma x and I2 comma x and go to of Im comma x, it is all going to be same, because whether it is going to be I1 comma x or I2 comma x or Im comma x, it is all referring to the same kernel, but there may be different lookaheads, but when we are combining them, they are all going to reach the same state. That is what if J is the union of I1 to Im, then the cores of go to of I1 comma x and I2 of x etc. up to Im of x will be same. Suppose if you are finding that K be the set of all items having the same core as go to of I1 comma x, then go to of j comma x is made as K. So, K is going to be the resulting set which is obtained with the same core. For the application of your go to of I1 comma x, then we will go for writing that is go to of j comma x equal to K. So, there are two things. So, one is that is how do you find out the action component, and another one is going to be how do you find out the go to component. As far as action components are concerned, So, these transitions defined for I will be repeated here, and the transition defined for j is also going to be repeated here, but we know that both will go to the that is same state provided I and j are combined in your LALR parsing table. But whereas go to are concerned, the same thing is being repeated, whether it goes for the ith state or for the jth state, we will put it as I comma jth state. This is how we are constructing the canonical LR look ahead LR parsing table from your LR of 1 items. So, first thing we will be constructing LR of 1 items, then we will find out the common kernels, and once the common kernels are obtained, we will go for combining the common kernels to produce LALR of 1 items, and once we are having LALR 1 items, by using this algorithm we will be able to go for the parsing table construction. We shall see one example, but after a short break. Welcome back. We have seen how an LALR parsing table is constructed from the given augmented grammar with the help of algorithm. So, now we shall see one example, that is how LALR parsing table is going to be constructed from the LR of 1 items. The grammar which we have taken here is this grammar S derives CC and C derives small c capital C or D. So, that is a grammar, it is a context free grammar, and now once it is converted into augmented grammar, we find that there are totally 4 number of productions available. With the first production S dash derives S, and the second one it is S derives CC, both it is variables, and C derives small c followed by capital C. First C is the lowercase letter and second C is the variable, and then C derives D. So, what we need to do first of all is the construction of LR of 1 items. So, we start with the closure of S dash derives dot S comma dollar. So, dollar denotes the terminator for the that is for any string whatever is recognized by this particular grammar, and first we will copy this into the resulting set, which is nothing but our I naught. So, S dash derives dot S comma dollar. So, now we have to find out the that is the closure of this by applying the rule. We find that S is to be expanded. So, when you find the expansion of S, there is only one rule, which is S derives dot C capital C, and now we need to compute the look ahead for this particular that is item LR of 1 item. So, it is going to be the first of beta comma A, and the beta here is epsilon, A is dollar. So, we will proceed with the first of dollar is dollar only, as we find dollar is a terminal. So, which that is what we are having dollar here, and now it is required to expand this C. The closure of C is going to be a non-empty set. There are 2 productions for C, one is C capital C, another one is D, and here we find that the first sum, that is our look aheads are to be supposed to be computed. So, the look aheads are obtained by the first set of beta A, beta here is capital C and A is dollar. When we concatenate both, we will be having beta as capital C, its first set contains C and D. So, we will be having the look aheads here as C or D, and once again C or D here. So, it is the first set obtained for the closure of S dash derives dot S comma dollar. So, now we need to apply the various transitions for this. So, the first one is we obtain the state number 1 by computing the transition for capital S. So, we get S dash derives S dot comma dollar. So, the job is done, because when you apply the closure of this, we will not be having anything else, since dot is on the rightmost end. There is no more there is item available for the closure of S dash derives S dot comma dollar. And when we compute the transition for capital C, it is from I naught. The first item is S derives C comma dollar. So, the application of go to will give you S derives capital C dot capital C comma dollar, and now we have to expand this capital C. There are 2 rules for that, one is C derives dot CC, another one is C derives dot D, and now we have to compute the look aheads for this particular items. So, by combining the first set of beta comma dollar, so beta is epsilon, so dollar will be the output, we will be having dollar and dollar here. So, that is I2, and then when you look at I3, we compute it for the small c as the go to symbol, that is transition for small c. We get capital C derives small c dot capital C comma c or d, that is from the source here. So, from here we get capital C derives small c dot capital C comma c or d. So, its closure is not going to be that is empty. So, we compute the closure of that. So, C derives dot C capital C comma C or D, and these lookups are obtained from the first set of beta comma A. Beta is epsilon here, A is C or D. So, you are having C or D, and the same thing is obtained for even C derives dot D comma C or D. Then I4 is go to of I0 comma D. So, you will be having C derives D dot comma C or D. So, now we are having the first 4 states, that is 5 states, so I0, I1, I2, I3 and I4. So, these are all actually obtained from the transitions for the state number I0. So, now we can find out the transitions even from, that is I2 for capital C, small c and D, then from I3 for once again the same thing, capital C, small c and small d, and from that we can find out the remaining states. So, we find that go to of I2 comma C gives us S derives capital C dot followed by a dollar, and the closure of this particular item is going to be empty since we find dot on the rightmost end. And when you look at I6, we have go to of I2 comma small c. So, for small c we are having C derives C dot capital C comma dollar, and the closure of this is going to be non-empty since we have dot followed by a variable. So, C derives dot C capital C comma dollar will be the output, and C derives dot D comma dollar, because dollar we get as lookup since beta A that is concatenation will give you empty followed by dollar. So, only dollar will be there. So, we will be having this, and then when you look at I7, which is obtained as a transition of I2 to D. So, we have C derives D dot comma dollar, and then we are having there is I8 obtained with the go to of I3 comma capital C. So, it is going to be capital C derives small c capital C dot C comma C or D. Then the remaining transitions, we have one more state called I9. We find it is obtained as a result of go to of I6 comma capital C, and C derives small c capital C dot comma dollar. The remaining states are already replication, that is go to of I3 comma C is giving I3, and go to of I3 comma D gives you I4, go to of I6 comma D gives you I7, and go to of I6 comma C is giving you I6. So, now we are having all the set of items obtained as a result of that is computing LR of 1 items. So, for the grammar S derives CC and C derives CC or D. So, once you know that the LR of 1 items are computed, now it is required to find out the various states and their there is commonality. So, among the different states what differs. So, if you find that the kernels are going to be same, they will be eligible for merging. So, if you are having, in this case we are having totally there is 0 to 9, that is 10 number of states are there. So, you can find around 2-3 number of states are having the common kernels. So, now look at the various states which are having the common kernels, and once we have obtained the common kernels, they can be merged to form the new set of states. We can go through that and find out what is going to be the common states here. So, there are totally 10 number of states available, and we have the state called 3 and 6. We can see it here. The first one is 3 is here. So, we derives C derives C dot C, C derives dot CC, C derives dot D, and when you look at I6, the same thing is available. C derives C dot C, C derives dot CC and C derives dot D, but what differs is here we have the lookup called dollar, and whereas the state number 3 we have the lookups C or D. So, as per the algorithm what we need is the set of items with common kernel, and I3 and I6 are eligible now for the finding the common kernels. So, we can go for combining them to form a new state called I36, where the new set of items are C derives C dot C comma there is C or D from the state number 3 and D from state number 6. So, we have a new state called I36, and the second item is C derives dot C capital C comma once again C or D from the state number 3, whereas dollar from state number 6. And finally, we are having the next item, that is C derives dot D, once again C or D from the state number 3 as that is lookaheads, whereas dollar is from state number 6 as lookahead. So, we have a new state called I36, which means in the new parsing table or in the new set of items, we do not have a new state called 3 and we do not have a state called 6, we will be having only a state called 36. So, it means that that is every action from the state number 3 and every action from the state number 6 will be now available only in the state number called 36. Similarly, if there is any that is state we get as that is output, maybe a state number 3 or state number 6, they all will be simply replaced by state number 36. So, in our parsing table there is no new state called 3 or 6, but there will be only one state called I36. And when you look at I4 and I7, so once again we find that I4 has a kernel called C derives D dot, and I7 is also having a kernel called C derives D dot, but in what way they are differing is only in terms of their lookaheads. In I4 we have the lookahead called C or D, and whereas in I7 we have the lookahead called dollar. So, we will be having the combination of there is all the three, there is lookaheads. So, we will go for a new state called I47 by the union of 4 and 7 to call it as I47, and where the new set of items are going to be C derives D dot comma C or D or dollar. And one more that is possibility for merging, it is from state number 8 and state number 9. So, we have a new state called state number I89, and the kernel is or the core is C derives C capital C dot. So, that is going to be common across state number 8 and state number 9, and now we can combine the state number 8 and state number 9 to form a new state called I89, and leaving no more state called I8 and no more state called I9, but the new state I89 with the kernel or the core, that is LR of one item, is going to be C derives C capital C dot, and lookaheads are going to be C or D or dollar. So, as far as the given problem is concerned, when you are constructing LR of one items, we had 10 number of states. So, now we have found that 3, 6 common kernels. So, we have combined them, and then 4, 7 we had common kernel, we combined them, and 8, 9 also we had common kernel and we have combined them. So, now we can think about how the parsing table is going to be that is constructed. Earlier we had that is 0 to 9, totally 10 number of states were there. So, now we are having only the states called 0, 1, 2, 3, 4, 5 and 6. Totally there are 7 number of states available. From the 10 states we have reduced the parsing table to only 7 number of states, and you can find out that there is no state called 3 or 6, but we are having 3, 6. Similarly, no state called 4 or 7, but it is 4, 7, and no state called 8 or 9, but we are having only 8, 9. But other than that there is no difference, only the actions are combined, and reduce actions if needed they are combined. So, you will be having the same set of actions, and already I mentioned that the difference is when you go for detecting the there is erroneous strings, there is a chance that it will take little more time than the time required for the canonical LR parsing table. So, that is about how we are constructing the LALR parsing table. To summarize, we have seen the drawback with the CLR parsing table and how we are overcoming that. That is, how do you go for a parsing table which is having lesser number of states than the number of states available in CLR. With the help of your LALR, have constructed new set of items by merging states where the common kernels are available, by producing or duplicating the there is lookaheads available in the states where the common kernels are obtained. So, that is about how we are constructing the LALR parsing table. So, you may be given there is grammars like this, there is LALR parsing table for this kind of grammars. So, we need to construct LR of one items and then combine the kernels, and then we will be able to construct the parsing table. So, that is about your LALR parsing table. So with this I complete this episode. Thank you all.